Swayam Prabha. Digital India. Educated India.
Hello and welcome back once again to this lecture series on aluminum based alloys and metal matrix composites. So, we have just started discussing about the properties of composites, and in the previous lecture we have seen how a particular property of a composite can be estimated from the properties of the individual constituents by using the rule of mixture. Okay. So, rule of mixture, as we have discussed, basically gives the weighted average of the properties of the individual constituents to give an estimated property for the composite with a given set of constituents, in which we have a metallic matrix in this case and a reinforcement. Okay. So, in a fiber reinforced composite, we have seen that if the volume fraction Vf is known, okay, then the property of a composite, for example, let us say the elastic modulus, can be estimated by this rule of mixture equation that we have over here. So, it goes by this particular relationship over here, and as I said, this is basically the weighted average of the properties of the individual constituents of the composite. Okay. So, if we know the volume fraction of the fiber, any property like elastic modulus or any other property can be estimated using that information, using the rule of mixture equation that you see over here. Okay. So, we discussed about the rule of mixture and derived it. So, now let us move on to the deformation behavior of a composite material. So, let us again take this fiber reinforced composites and then see, as it is loaded in a particular direction, how the material deforms in terms of the deformation behavior of both the constituents. Okay. So, we are going to consider these fibers aligned vertically and loaded in the same direction, in the direction of the fibers. Okay. So, if you look at the deformation behavior or the stress strain curves for the constituents, that is the matrix and the fiber and that of the composite, it would appear like this. So, this is the matrix which is soft and ductile. Strength is low, but the ductility is high. And if you are talking about a ceramic reinforcement, it is completely the opposite. It is stronger but brittle. there is no plastic deformation at all. Okay, the plastic deformation is almost nil before the fracture. So as I said before, the property of the composite will be in between these two, and therefore the stress strain curve of the composite will lie in between these two curves, like this. Now, if you look at the deformation behavior, three stages of deformation can be defined. First stage is the elastic deformation, where both fiber and the matrix are elastic. Both fiber and matrix deform elastically. So that is stage one. If you look at the stress strain curve of the composite, so that is the straight line portion or the elastic portion, right? So that is stage one. And then as you increase the load, it enters into stage two, which is quasi-elastic in the sense the fibers are still elastic, but the matrix starts to deform plastically. So while in stage one, the elastic modulus can be obtained by the rule of mixture because both are in the elastic limit. But here the matrix has gone into the plastic deformation stage and the fibers are still elastic, right? So here in the rule of mixture equation, the elastic modulus of the matrix has to be replaced by the slope of the stress strain curve of the matrix material, that is d sigma by d epsilon. And since the slope is generally much smaller than the elastic modulus, equation 2 can be written as this, because this term now can be ignored. So in this stage, in stage 2, if you unload the composite material, the fibers will return to their original condition, but the matrix will still retain some plastic deformation, and as a result of that, the matrix will be under compression, right? because it is still trying to hold on to that permanent deformation which it has already gone through, but the fibers are trying to pull it back, right? So as a result of that, it will develop some compressive stress on the matrix, right? So the deformation will be quasi-elastic in stage 2, right? The composite will respond as a quasi-elastic material when loaded. Now in stage 3, when you increase the load further, both the phases, both matrix and the fibers now can deform plastically. So in the stage 10 curve, it will be the upper portion, right? So from here onwards, after stage 2, this portion is the stage 3. So here the composite strength in this particular stage, the composite strength sigma Cu will be given as the ultimate strength of the composite will be given as this. So at this stage, the fibers can fracture. So this is the fracture stress for the fibers. And sigma m prime is the flow stress of the matrix at a strain corresponding to the fracture stress of the fibers. Right? So in order to obtain any benefit with regard to the strengthening that the fibers could impart, there has to be a critical volume fraction of fibers beyond which the strengthening effect can be obtained. Okay, if it is below that critical volume fraction, below that critical amount, then you may not get the strengthening from the fibers. Okay, so when the strengthening occurs, you could expect that the ultimate strength of the composite should be greater than or equal to that of the matrix, which is given by sigma mu. Okay, so now if we replace sigma cu by this expression, we can write this equation now. And in terms of the volume fraction, FF, we can write as So the critical volume fraction Fc will be given as so in order to derive any strengthening effect from the fibers, the volume fraction has to be more than this critical amount. Okay, then only you can expect to have some benefit in terms of the strength. And if the volume fraction of the fiber is small, then you can expect the fibers to break because their amount is too low to carry the load. So as you increase the load, the fibers will start to fracture, right? Which means this will be sigma f will be 0, and we can write this. Okay, so this will lead us to a minimum volume fraction which is needed for any strengthening effect from the fibers. So now if I replace sigma Cu from the previous equation that we have, that is equation 4, then we can write and the corresponding volume fraction under this condition, when this occurs, will be given as this by rearranging this particular equation. The minimum volume fraction of the fibers can be obtained as this one. Okay, and in fact this can be shown in terms of a plot also. Both F critical and F minimum can be shown in this plot. If you plot the strength of the composite against the volume fraction. So strength of the composite as we have seen before, is given by this equation 4 that we had before. So let me rewrite it over here. And if you plot this as a function of the volume fraction, then you would get a straight line like this. So therefore, this intercept will be sigma m prime, as you could see from this equation, when ff is equal to 0. And this end will be the fracture stress of the fibers when ff is equal to 1. Okay. And if you plot this equation here, then you will get the F minimum from the intersection of these two lines. Okay. So this equation will also give you a straight line, equation 6. So let me also rewrite equation 6 over here. So when ff is equal to 0, it is simply the ultimate tensile strength of the matrix. That means this intercept is sigma u or sigma mu, right, as you could see from here. And when the volume fraction is equal to 1, then this becomes 0, as you could see from here. Okay. And the intersection that you have between these two lines, that represents the volume fraction corresponding to that represents the minimum volume fraction of fiber which is needed to obtain any strengthening effect. Okay. And if you draw a horizontal from here, from this point on this line, then the corresponding volume fraction is the critical volume fraction. Right, so this is how the minimum and the critical volume fractions of the fiber can be represented by a plot like this. If you plot these two equations as a function of the volume fraction of the fibers. So let me quickly summarize. The property of a composite can be given by the rule of mixtures, which basically represents the weighted average of the properties of the individual constituents. So if the volume fraction of the reinforcement is known, then the property can be obtained by this expression representing the rule of mixture. Okay. But one thing I should mention over here is the fact that rule of mixture will always give you the upper bound. And generally, the experimental values will be lower than the value which is obtained by rule of mixture. This is because of the fact that there are some assumptions which are made in the rule of mixture. For example, this isostrain assumption that we made, that is strains in the fiber as well as the matrix are taken as equal, but practically that is not true. A fiber is a completely different material from the matrix, and therefore at a particular load you cannot expect the strain to be same, right? So that is one assumption because of which the experimental values and the values obtained from the rule of mixture will differ. And the other thing which is not taken into consideration in the rule of mixture is the fact that there may be presence of defects. That is not considered in rule of mixtures, right? So if there are presence of defects, obviously the measured value will be lower, and that is why, as I said, the experimentally measured values are generally lower than the values obtained by rule of mixture. And then we talked about the deformation behavior of a fiber reinforced composite, and we have seen that it goes through three stages. The stage 1, which is the elastic stage, where both the fibers and the matrix deform elastically. Then as you increase the load, it enters the stage 2, which is quasi-elastic in the sense that the matrix deforms plastically, but the fibers are still elastic. And then as the load is further increased, it goes into stage 3, where both the fibers as well as the matrix undergo plastic deformation. And at this stage, if the load is high enough, the fibers will also break. Okay. And ultimately, the composite will fracture. And considering this deformation behavior, we have in fact derived a critical volume fraction which must be exceeded for any strengthening to occur in the composite due to the presence of the fibers. Okay. And then we have also derived a minimum volume fraction of the fibers which must be added for the strengthening effect to come. And both of these can be represented in a plot like this, in which the composite strength is plotted against the volume fraction of fibers. So with this, we come to the end of this lecture, but I will see you soon in the next lecture. Keep watching.